Hey guys, we're going to be working on example 30.4 out of the textbook, which is a basic problem dealing with two parallel conductors and a third conductor that they're kind of resisting. Let me show you. Here's an attempt at a 3D drawing, but we have two conductor lines here on the ground. These are just two wires. Then we have a third one levitating above it like that. This is creating like a triangle right here. So that's levitating in the middle of the two of them. These actually go on this way, but the wire on top is finite. So we could also look at it from this angle here, kind of dead on here, and look at some of our basic forces here. We have a force of gravity pulling down this way, and then we have the electric field pushing up this way to the right, and this way to the left. Actually, let's switch these, because this is the left one, that's the right. So we know that this force is coming from the left side, and this force is coming from the right side. Let's also label all of these sides A, and this angle theta right here. And this is our current I running through it. I is running in this direction. So what we'll first want to do here is look at the equation of force for two parallel wires here. So because we have two of them, put a 2 here. And then we have the currents. Oh, I forgot to mention. The current on this top rod is moving this way, but the current on these rods are moving. I know this is kind of confusing. I will color these in to make it a little bit better here. That might not even help. But these are the currents moving in this direction right here. Of these two are moving that way, this one's moving this way. So let's label this 1, 2, 3. The currents of 1 and 2 over pi a, the area, times the length, is cosine theta. Theta is the angle of difference that these are projecting it at. So we also have the force of gravity in play pulling this wire down. It's going to be, of course, minus mass times gravity. We also realize that this is going in the k-hat direction. So then we can do the summation of forces, which is equal to 0. It's equal to 2 I1, I2, pi a, L cosine theta, minus mass times gravity. Then all we need to do is solve for, oh, you know what I forgot here? Mu 0, permeability of free space constant. Very important. Then all we need to do is solve for I2. So what we'll do is put mg on the side here for now. Actually, never mind. Yeah, let's move. This is equal to mg I2. So we'll add mg to both sides if this is equal to 0. Add mg to the other side, then divide by L cosine theta, as well as I1, the constant, and 2, and then pi and a go on the top. Let me double check that real quick. Yep, looks good. This is I2 right here. So then all we need to do is plug in values for these. Forgot to provide these values earlier, but we know that A is equal to 0.01 meters. The length L is equal to 10 meters. The mass is equal to 0.4 kilograms. And the current I1 is equal to 100 amps. So then we'll just need to plug these in. Mass 0.4, gravity is 9.8 meters per second, it's kilograms. Pi times A, which is 0.01 meters, over, we'll start with the permeability of free space constant, 4 pi times 10 to the minus 7 times the current 1, which is 100 amps, times the length, which is 10 meters, times cosine theta, which, because this is an equilateral triangle, theta would be half of 60, so it would be cosine 30 right here. And then once we solve this all out, it should be equal to 113 amps. Pow! Yeah.